Okay, let's continue with section 2.2, the surface integral. So, continue with the line integral described in the first section. Here we are discussing the surface integral. So, as the name suggests, we try to calculate the total field passing through a surface. So, as the figure suggests, as the figure to the bottom right suggests, the surface delta S is facing to upper left, as the normal direction arrow indicates. And there are some background magnetic flux P passing through it. However, the two vectors, the normal vector of the surface and the magnetic flux density vectors, are not in parallel. They have an angle of alpha. So as a result, the integration can be regarded as not all the magnetic flux passing through the surface counts. Only part of them are accounted. So we need to find out the components that is effective for this surface integral. So as you can see from the right, you can be decomposed into two components. One is normal to the surface, normal to the, one is orthogonal to the normal direction of the surface, which is the green arrow components. And the red arrow component is in parallel with the magnetic flux. So it should be accounted. So as a result, we should add a factor that is cosine alpha. So to find out the effective projection of the magnetic flux density onto the normal direction of the surface. So B cosine alpha is the one that should be included in the computation, while the B sine alpha, the component of magnetic flux density B that is orthogonal to the normal direction of the field, should not be included. So in other words, if the surface normal direction align with the field, then you can include most of the field, includes all the field. On the other hand, if the normal direction of the surface is perpendicular to the field direction, then the field, the background field, will produce no effect onto the surface, all right? Okay, so in this slide, it's again address the effective part necessary to be included in the surface integral. 所以要了解的就是说你的背景的磁场啊，或者是像这个例子是磁动量嘛，或者其他的那个场，在我们在做面积分的时候要搞清楚了不是通过那个面的都算，而是跟那个面的法线方向平行的部分是在这个面积分里头被算要被包含进去的垂直的部分就没有用不会被纳进去，所以你可以把它看作是回圈，你可以把它这一个 cosine alpha 的这个操作这个 cosine alpha 的操作看你怎么写了以这种写法，小括弧括在前面的话，那你等于是说，把磁通量密度里头有效的投影到 delta S 的法线方向，那上面的分量当做有效的投影量那你也可以把这个小括弧括在 delta S 跟 cosine alpha， 那就表示说，跟这一个，也就是说变成是说这个面垂直于 B 的这个方向的这个投影量那当然。不管是谁投影到谁，它都会变得比较小 变得比较小，因为是 cos alpha 的关系嘛，所以 alpha 等于cos alpha 值都是小于等于1嘛，但当 alpha 等于0度的时候，也就是你的面法线方向跟场的方向是平行的时候，你可以得到最大的这一个最大的这个量，面积分的这个量 ，OK。所以这边就我们刚刚讲的，看你把小括弧括在哪边，它有不同的解释方式，但结果是一样的啦，Alright, and here is an example. This thing is referred to as the loop antenna, and it's mostly used in well for this case it's used for AM radio reception. AM radio reception. And the reason why is AM radio. Do you know the frequency of AM radio? Well, you may have heard of AM, but you probably nowadays not many people use AM radio receiver, right? Okay, so the frequency band of AM is about 500 kHz to 1600 kHz. So you can say it's roughly about 1 megahertz. So what is the wavelength of 1 megahertz? Wavelength of 1 megahertz. The speed of light is 3 times 10 to the 8 divided by 1 mega, that is 10 to the 6. So the wavelength of 1 megahertz is about 300 meter. And to make an effective antenna, if you use the conventional dipole antenna or monopole antenna, the size of the antenna should be about half the wavelength or at least a quarter wavelength. So if you take M signal into account, the frequency is 1 megahertz and the wavelength is 300 megahertz, about 300 meter. You should have a dipole antenna of about approximately 150 meter, which is way too big for a radio receiver. All right. So we use loop antenna to do that. How does it work? Say, from the radio station. So radio station has a tower, and somehow it managed to generate electromagnetic wave. And the electromagnetic wave from the tower. So suppose, assuming that the microphone I have in hand is the radiating antenna. So the electrical field is going up and down. Usually for ground wireless communication, the polarization of the electrical field is mostly going up and down, which is referred to as vertical polarization. So electrical field goes up and down. How about the magnetic field? Well, in your high school, you are probably, in your study of electromagnetics in high school, you probably know that the right-hand rule. Suppose this is the electrical field direction of your thumb. Your thumb is the E field direction. The index finger is your magnetic field direction, and the middle finger should be the wave propagation direction. So the wave generating out of the dipole antenna is going like this. And because the E field is on the vertical direction, the H field is on the horizontal direction. So what you need is have a loop antenna like this. Place it where? Place it, say, in front of, say over here, okay? Then, well, all right, so you should, so for a position away from the antenna, you have electrical field going up and down and magnetic field going left and right. So you can place your loop in this way so that you can intercept 拦截那个磁场，磁场是 只要你的往外辐射的电磁波是电场垂直的话，磁场就是水平的。然后你把那个路板antenna这个环对着 source 横着摆的时候，就可以拦截磁场。而拦截的磁场，因为它是一个时变磁场 time varying magnetic field. So from our discussion in section 2.3, we'll know that the time varying magnetic field will produce electrical field, will produce electrical current, will produce electrical current. This is the so-called Faraday's law, 法拉第定律。时变磁场造成电流，法拉第定律。Okay. All right. So in the previous slide is just a preview of what we will have in the next section. So now let's take a look at the procedure of the surface integral. So similar to our previous discussion about line integral, you first divide the surface to be integrated into many small surfaces so that you can handle curvatures. So the surface is not necessarily a flat surface. It can be a curvature, a surface of any shape, such as this one. So the normal direction at the different positions are not necessarily the same. They can go at a different direction. So you divide a large surface into two small ones. How small it is? How small it is? It should be small enough so that all the normal direction on this small surface can be approximated by a single vector. So which means the small surface should be small enough so that it can be approximated as a flat surface. Alright, so that you can use just one normal vector to represent the direction of the surface. 所以什么叫？所以数值的这个积分，它的精要就在于说，你要积分的范围切得够细。什么叫够细？细到在那一个小范围里头，假如是线段的话，就可以被趋近于一条直线；假如是面的话，就可以被趋近于一个平面。这样子的话，你就可以用单一的一个法线向量来去代表它。Then you can calculate the field intercepted by this small surface individually. Then sum all the contribution from those small facets, small surfaces, to add up the total field effective for this surface of any shape. All right. So for each individual surfaces, you need to write up the normal direction vector of that surface, as well as the magnetic field vector, magnetic flux density vector in that specific region. Then the contribution of the field passing through this surface can be found using this equation. So here you have delta phi. Phi is what? Phi is magnetic flux, 磁通量。BA 磁通量密度magnetic flux density. And delta S is the surface, one small facet, one small surface, one small piece of the surface, and cosine alpha J is the cosine value of the angle between B and delta Sj, Bj and delta Sj, all right? So the total magnetic flux phi passing through this larger, more complicated surface can be found as the summation of individual calculated flux, like this one. All right. Okay, so it's pretty much like what we have for a line integral. And note that the product of the magnetic flux density and the differential surface 忘记了，所以这个叫做 differential surface 嘛，就像前一我们在讲拉因的时候，那个 delta L 叫做 differential length， 这边 delta S 叫做 differential surface， 意思就是一个很小很小的平面啦，当然小到它可以被用当一个向量来去表示它的整体的方向，接近一个平面So have you noticed that on the blackboard I write the magnetic flux density as a vector? And how about the magnetic flux? Magnetic flux is a scalar. Why? Because it's the product, is the dot product result of delta S and B, which are all vectors. And the dot product of the two vectors becomes a scalar. So magnetic flux phi is a scalar, while the magnetic flux density is a vector. Should be careful about that. And here's a numerical example. So in this region, for your convenience, this is a flat region. So the region extends from s equal to 0 and 1 and y equal to 0 and 1. So it's a flat surface. And what is the normal direction of the surface of these 25 pieces? Well, they are all aligned to what? Positive z direction. Okay? No, positive z direction. And however, the magnetic flux density passing through this region are different because B equals to 3 times x times y to the square. And it's pointing to the positive z direction. So the magnetic flux density B is a function of position x and y. So you need to substitute the x coordinate and y coordinate to compute the magnetic flux density at the individual facet. All right. So you can write up, in this case, on the textbook, it uses the middle point, the center of the facet, to find the magnetic flux density. So it says 2 times j minus 1 times 0.1 is the width, okay? 2j minus 1, okay, so I ranges from 1 to 5 and j ranges from 1 to 5 as well, all right? So what is the benefit of choosing the center to find the magnetic flux density? Well, the accuracy is better, right? So as what we have talked yesterday, you can choose anywhere in the facet. You can choose this corner or this corner or this corner. As long as the number of facets becomes larger and larger, it doesn't matter if you choose the center or the corner. However, in this case, this is a relatively coerced division. coerce 是什么？很粗略的嘛，所以切的没有很细所以选中间一点的话，会让精确度高一点嘛因为毕竟你那个3倍的 xy 平方，其实跟它的位置的敏感度还蛮高的OK， 所以选中间那一点的话，会算的比较准一点 ，right？ Okay, so for individual facet, the Bij at the center of the facet can be written as 3 times 2i minus 1 times 2j minus 1 to the square times 0.001. Alright, so that's the magnetic flux density passing through the small facet. And the size of the facet are the same for these 25 regions, which are 0.04. And now that they are all aligned to the positive z direction. So substitute all the known quantities into the equation of the summation for this solving integral. We can find out the total magnetic flux passing through the surface is 0.495 Rep. Okay? So you can guess, is this underestimated or overestimated value. Of course, you can perform surface integral using an analytical approach. You can do the exact calculation of the surface integral and find out the exact value. Okay, so let's do that. Okay, but so before that, I already mentioned that the more division you have, the more accurate the result shall become. And to execute surface integral, it can be regarded as two-line integral because a surface is two-dimensional geometry. When it is expanded by two line vectors of different directions. So the surface integral is in fact a double integral because ds is equal to the product of two differential lengths. All right, so let's carry out the computation. So here is another representation, which is a more commonly used representation of ds, or of differential surface. The differential surface can be regarded as a product of the two differential lengths and vector, the normal vector representing the direction of the surface normal. So in this case, the ds is expanded by location differences in the x direction and y direction. So you have dx dy, and the surface always pointing to the positive z direction. So you can write up as dx dy az. All right, and the dot product of b and ds is this. 3xy to the square az dot dx dy az. And fortunately, because this is a dot product, so the az part goes away and it becomes a scalar. So the integral can be turned into a double line integral. A double line integral. So in this case, it performs line integration along the y direction first, so as the limit suggests. We integrate from y equals to 0 to 1, and then integrate from x equals to 0 to 1. So by doing this, which shouldn't be difficult for you guys, the result is 0.5 rep. Okay, comparing the previously numerical integration result, which is 0.495, the error is about 1%. So from my own perspective, in my own opinion, I think this is a pretty good estimation. With relatively accurate, with a pretty good accuracy. The error is with just 25 division. The error is about 1%, right? And of course, if you have more divisions, the error can be further reduced. All right, and for the case shown here, I would like to remind you that this surface comes with edges. So another surface type is referred to as closed surface, which are surfaces without edges. For example, the surfaces formed by this bubble. Can you tell me where are the edges of the surfaces of this bottle surface? 所以我们今天谈到的观念是封闭面跟非封闭面。刚刚的例子的话，它有明确定义的面的边缘，所以它不是封闭面。而在电磁学里头呢，我们常常会处理到所谓的封闭面所以就像封闭回路一样，封闭面的表示也是用那个圈圈，有没有看到？So to indicate that we are trying to perform the surface integral of a closed surface, we add a circle on the integral symbol, right? So this circle suggests that the surface is the closed surface integral. So what is the physical suggestion, physical significance of this function, of this representation? It tries to find out the total magnetic flux coming out of a closed surface, coming out of a closed surface, right? As I already mentioned at the first week, I guess, I told you that if this is not a closed surface, for example, a piece of paper, then what is the surface normal direction? It can be goes up or goes down from the surface. You can have positive and negative normal direction. All right. On the other hand, if you have a closed surface, such as a balloon or a bottle, they form a closed surface, then the surface direction is the outward direction. So imagine that the origin of the coordinate system is enclosed by this closed surface. Then the surface direction is pointing outward. 所以封闭面的话，它的方向就是单一的，朝外的，也就是朝那个穿出这个封闭面的方向。那这一里头的这一个式子写作磁通量跟面积的那个封闭面积跟那个面的封闭面积分，指的是什么？它要去计算的是从这个封闭面跑出去的因为跑出去为正嘛正的方向是往外的方向，所以它要计算的是穿出封闭面的磁通量总量。OK？ So here's an example, all right? So we have a function describing the magnetic flux density in this region, B equals to x plus 2 in the x direction, 1 minus 3y in the y direction, and 2z in the z direction. So you see the magnetic flux density is a function of position, and it's dependent on all the three coordinates, all right? And the region to be evaluated is a closed surface formed by 6 corners, 8 corners, okay? So you have 8 corners, forms 6 surfaces, 6 flat surfaces as a cube, all right? So to find out the magnetic flux emanating, emanate, E-M-I-N-E-T-N-E-A-T, emanate. EE3 吧，是吗？穿出去的往外的emanate To find out the magnetic flux emanating from this cubical area, cubical surfaces, you can divide the closed surface integral into 6 surface integrals. So here is the one formed by point ABCD, which is the surface facing toward the back. EFGH is the surface facing toward the front, to the right-hand side, to the left-hand side, to the top, to the bottom. Okay, you have 6 surfaces. So let's begin with the surface ABCD. All right, so that's the okay. From my own slide, I try to add some color on the back surfaces, but it's apparently not shown in the screen. All right. So substitute the coordinate value here into this form, because here we have what? We have x equals to 0, y vary from 0 to 1, and z vary from 0 to 1. Okay, but x equals to 0. So substitute the known condition x equal to 0, b becomes this thing, and the ds. Now that Steve, you can understand why it is written in this way. ds equals to minus dy dz ax. dy 是什么 ？dy 是它横向的嘛 ，dz 的纵向的。那这负号是哪来的？负 负号是这个面的方向是朝后的，啊，所以看一下它的面的方向是往负 ax 方向，啊，所以这个负号是负 ax 的意思，啊，所以它的展开是 dy 跟 dz， 但是它的方向是朝负 ax 方向，所以 ds 要写作这个样子。所以把这个东西跟前面的 b 去做内积的时候，事情变得比较简单了。为什么？因为面的方向是 ax 方向，所以这里头呢，后面 y 方向的分量跟 z 方向的分量都没遵守啊，所以只有 x 方向的分量，所以变成是负2的 dy dz。而这一个结果，这个 integrand 呢，拿去做面积分的时候，其实就是2次的线积分，让它沿着 y 方向积分一次，再往 z 方向积分一次。那因为这边是一个负2的常数，所以你的积分结果相对简单嘛，就等于负2啊，因为 y 等于0到1 ，z 等于0到1。那 the similar method can be applied to the other 5 surfaces. So you can find out the magnetic flux going to the front, goes out of the front is 3, and to the left is -1, to the right is -2, to the top is 0, to the bottom is 2, and you can find out the closed surface integration of this thing is this, and equals to 0, right? Equals to 0. What is the significance of this result? This indicates or this verifies that the magnetic flux density expressed in this form is a legitimate magnetic flux density. 这个结果告诉我们的是，这一个磁通量密度的表示是合法的。也就是说，你这边所看到的磁通量密，这个我说它是磁通量，题目说它是磁通量密度 （magnetic flux density）。而假如它真的是符合 magnetic flux density 的话，那么对于一个封闭面来讲，它的封闭面的面积分，所有进去或者是出来这个封闭面的磁通量必须等于0，必须等于0。这个结果其实是我们现在 section 2.2 嘛，2.3、2.4、2.5，我们在讲高斯磁场定律的时候会再来谈这件事情。也就是说，任何封闭面进出的磁通量必定为0，必定为0。那为什么会这样呢？因为我们没有独立存在的磁核。我们有独立存在的电荷嘛，对不对？同意嘛？我们有独立存在的电荷，那电荷的电场分布长什么样子？这边一坨电荷，那它的电场长什么样子？有没有看到？有看到嘛？像刺猬一样放射状跑出来嘛，对不对？所以你只要在这一个电荷的周围用一个 balloon， 用一个气球把它包起来的话，然后你去算它穿出去的电通量。会等于0还是小于0？好吧，反正不等于0嘛。假如说你里面有电荷，我刚刚那句话就把 Maxwell equation 的第3条高斯电场定律讲完了。OK， 积分形式的高斯电场定律其实讲的就是说，对于一个封闭面来讲，只要这个封闭空间里头有包住电荷的话，那么它的电通量密度的封闭面积分会不等于0。反过来，因为我们没有独立存在的磁核，或者说你已经知道的一件事情是磁力线都要绕一个完整的圈圈，对不对？即便是你手上有一个磁铁，这边有一个磁铁。你没有看到这个磁铁所跑出来的磁力线？你可能天性不够哦，不适合修我们电磁学哦。有没有看到这个磁铁这边是北极，这边是南极 ，N 跟 S。有没有看到磁力线怎么长的？OK， 我们班上总是有些同学比较有悟性的OK， 有看到了OK。好啊，所以你有看到那个磁力线怎么长的？那你在它旁边试着加一个封闭面，而这个封闭面你会发现有进就有出，所有的磁力线 进去这一个封闭面的磁力线，比如我在这边，我在这边加一个 balloon， 加一个圆球，又加一个立方体，会有磁力线从上面灌下去嘛？因为磁力线从北极跑到南极，那事实上在磁铁里面的时候，会用从南极跑到北极嘛，所以它会绕一圈。所以多少进去，其实就会多少跑出来。就像20年前的港片讲的出来跑的总要还的，对不对？我看我是用英文讲好了，中文讲会讲太多笑话。OK。上英文讲比较快一点，省掉那些笑话。OK。好了，所以当我们在看这个封闭面积温的时候，其实以磁力线好，所以回到这个结果，当你的磁通量密度的封闭面积温等于0的时候，至少我们比较安心因为题目说它是磁力线，然后看起来它是遵循这个规则的，多少进去就多少出来。假如说你的磁力线是形成有单离回圈，而你没有像电荷一样那种单独独立存在的磁核的话，那么就会是这个结果。OK， 好，2之2教完了。